printed circuit board ground plane heating. The printed circuit board contains the electric layer and the conducting ground plane, and some elements connected both to the power bus and the ground plane. Most elements have low power, but one element consumes electric current of 10 amperes. Then the current flows to the ground plane and along the ground plane to the earthing place. Our task here is to calculate the board heating. The element is located at some distance from the board, so it doesn't affect the temperature distribution in the board. On the left is the top view of the board, and these holes are the connection place of some circuit elements. At this hole is the 10 amperes current inflow. At these holes the board is grounded. You might guess that electric current distribution is not uniform, and the same is true for the losses. So our first task is to find the electric current distribution and loss distribution. Later we will calculate the temperature distribution. The ground plane thickness is only 35 micrometers, so we can adopt two-dimensional electric analysis. Let's start QuickField now and simulate DC conduction problem. In QuickField I create new problem. PCB electric. Next. Problem type is DC conduction, as I have DC current. Model class is plane parallel and the model thickness is 0.035 millimeters. Okay. On the left you can see the problem pane, and on the right you can see the geometry model editor window. Here you can draw the geometry model, or you can import the geometry model from the .dxf file. .dxf file is used by the majority of the CAD systems to interchange two-dimensional geometric models. So here I have the file already prepared. Open. Here you can see the ground plane. To distinguish one geometric object from another, we should assign labels, and through labels we also assign physical properties. Switch to select mode and click to select a block. Open the properties dialog and type in the label name. This is the copper. Okay. There is no electric current in the holes, so I do not assign labels to these holes. For the copper I specify electric conductivity, which is 56 megasiemens per meter. Okay. Now let's assign labels to the boundaries. At the second hole we have electric current inflow. I select it with the rubber band. Open the properties. In fact, this time I have selected bodies, edges and vertices. As I said, there is no electric current in the holes, so I assign properties to the edges. The label is I+. Okay. And these two holes are grounded. So this hole and this hole are grounded. Use the control button pressed to select multiple objects at the same time. Properties, again I follow to the edge stop and assign the label grounded. Okay. Now for this label I specify 0 electric voltage, and for this label I should specify normal current density, which is current 10 amperes divided by the cross-section area. Well, the cross-section area is a side surface of the cylindrical hole, which is 2 multiplied by P multiplied by radius multiplied by plane thickness, which is 0.035 millimeters. Now I need to find the radius. Right, radius. Okay, let me check. I will zoom in, switch the zoom in mode off, click the edge, open properties, and the radius is 1.10 1.1049 times 10 to the power of minus 3. Now this would be the normal current density. Okay. Zoom to fit. Model and data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all simulation files and run the analysis. The problem has been solved. Let's take a look at the result. Here you can see the current density color map. You can adjust the field picture and switch on the equilines of potential. You can switch on the vectors of the current density, and you can see the color map of the power loss. As you see, the power loss distribution is not uniform. Here you can see the color map, and on the right you can see the relation between the colors and the values. In fact, you can measure the losses in any point. To use the local values tool, click any point and get the number. Power loss, electrical conductivity, electric potential, current density. And to get the total power loss, you can use the contour tool. Just click to select the entire board, follow to the integrals, and click joule heat in a volume. These are the total loss in the ground plane. And let's check the current value. Again, I will use the contour tool and draw the contour crossing the current paths. Now follow to the integrals, current through the surface. Indeed, it is 10 amperes as we have specified. Okay, we have found losses. Next task is to calculate the temperature. To calculate the temperature distribution, I create a new problem. PCB heat. Next. Problem type is steady state heat transfer. Model class is plane parallel. Model thickness is 0.035 millimeters. I plan to transfer losses distribution from electric to thermal analysis. To enable automated data transfer, both problems should be based on the same geometry model. So here I click in the geometry and press the browse button and look for the geometry model file that was used in a DC conduction problem. PCB electric.mod. Here it is. Open. Finish. Now the geometry model is the same in both problems and the labels are already assigned, but here in the thermal problem we should specify thermal properties. For the copper I specify thermal conductivity, which is 380 watts per Kelvin meter. And I specify zero losses. The losses will be transferred from electric problem. Okay. We should specify natural convection boundary condition on the board faces. I will select faces of the board, follow to the properties and assign the label convection. For this label I specified the convection boundary condition with the convection coefficient of 10 watts per Kelvin meter squared and the ambient air temperature of 20 degrees Celsius. Okay. There is no specific conditions to assign for the source and for the drain and for the holes, so I double click the label and do not enter any values and click OK. Now you see the label has the 0 mark, which means there is no physical properties assigned to this label and this label should not affect the results. The same for the E+ label. Now let's set up the link. There is no yet any link between electric and thermal analysis. Follow to the problem properties, switch to the links tab and choose the data type, generated heat. Browse for the problem. The problem should be PCB electric. Here it is. Open and add the link to the data sources. Now the link should appear here in the tree. Now power losses calculated in electric problem will be automatically transferred to the thermal problem. Let's save all simulation files and run the analysis. And we get the error. The linked problem results are out of date. What does this mean? Remember, both problems share the same geometry model file, and I have modified the geometry model. I assigned new label to these edges, and I have specified physical properties to this label in thermal problem, but I have not assigned any properties in electric problem yet. So I should go back to electric problem, and for this label, in fact there is no specific physical meaning in this label in electric problem. So again I don't assign any values here, just open the dialog, click OK, and you see the 0 mark next to the label name, which means again that this label doesn't affect the results. Anyway, the problem setup has changed and the geometry model has changed. We should run the analysis again. Solve. Yes, save simulation files. Let's make sure that the current value is the same. Again, I will use the contour tool. Current, the same 10 amperes. Okay, let's run thermal analysis. This time no error message, and we can see the results. Well, the fact that we do not have error message doesn't mean that the results and the problem setup is correct. We have the temperature values which is much too high for the reality. Let's think what we have missed in our model. Let's take a look at the picture again. We have specified convection from the side surfaces only. At the bottom we have the dielectric layer with low thermal conductivity. But what about the top side? We have not specified convection from the top side. Let's go back to... This is the top side. Click it. It has the label copper. There is no way to specify convection from the top surface, because in plane parallel geometry we have only side surfaces. But there is a trick that can help us to keep the model simple and physically correct. By simple I mean two-dimensional. Let's take a look at the picture again. The heat flux from this top surface is a product of the convection coefficient multiplied by the temperature difference. Units are watts per meter squared. Instead of the convection heat flux, we can specify negative power in a volume, which units are watts per meter cubed. You see, flux from the area, power in the volume, and the volume is a product of area and the plate thickness. So we should use the plane thickness to convert the convection heat flux to the power. Okay, let's go back to QuickField, and here I should specify negative power source, which should depend on the temperature. So I click depends on the temperature. If the plate temperature is 20 degrees Celsius, we have zero convection flux because the air temperature is 20 degrees too. So the power source is 0. Okay, but if the temperature is 220 degrees, heat flux would be 220 degrees minus ambient air temperature multiplied by the convection coefficient, which is 10, and the volume negative power would be heat flux divided by the plane thickness, which is 0.035 millimeters. Okay, let's calculate 120 minus 20 multiplied by 10 divided by 0.035 and divided by 110. This is the volume power density. Looks like a very big number. Anyway, let's try it. Minus 28.37 times 10 to the power of 6. Okay. Let's run the analysis again. Let's take a look at the results. Now these values seems reasonable. The ground plane temperature would be between 23 and 27 degrees Celsius. This example was offered by Mr. Niels Forsström some 10 years ago when QuickField was not capable of three-dimensional electric and thermal analysis. Now QuickField can do both, and three-dimensional electric and three-dimensional thermal analysis. And if you search our website for the PCB heating, you can find this example page. Here you can read about problem setup, browse the solution section, take a look at the results, and download the simulation files. Simulation files can be opened and results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free. In the next examples I will demonstrate to you how to do this similar task in 3D.